Here, I am Ms. Kritika Pathe, a PhD student at ICT, and I am going to be the host of today's session. The session that is going to be conducted today now is the protein aggregation and biophysical characterization, and we have very esteemed guests with us, dignitaries with us to share their valuable knowledge and information with us. And it's indeed a great honor for us to have you all over here, all the attendees, all the delegates and all the speakers. Moving forward, I take the opportunity to welcome the moderator of our today's session, Dr. Navratna Vajpayee. To share some information about him, Dr. Navratna Vajpayee is the Chief Scientific Manager in R&D in Biologics Limited. He did his PhD in Structural Biology and Biophysics from the University of Basel. His core expertise lies in solution NMR spectroscopy, hit validation, protein folding phenomenon using high pressure NMR methods, fragment-based drug design, FBDD, and elucidation of structure function mechanism of disease-related proteins using NMR. He carries over 12 plus years of research experience. I request him to come up, and the stage is all his, and he is going to conduct a further session. Thank you, sir.
Thank you, Kritika. Thank you to the audience, Ratnesh, and all the students in the lab for conducting this Biosimilar Workshop, especially in Goa, so that all of us are here. So protein aggregation, the title of this session is actually protein aggregation and higher order structural characterization. This field has evolved in the last 20-30 years, and we all know that these proteins are produced through recombinant DNA technology, which is done through different expression platforms. And while doing so, we have to address multiple quality attributes. Some of those quality attributes are extremely critical, mainly because they are associated with the function or the immunogenicity response which they can create. And therefore, it is absolute must that we do our best to do a detailed characterization of those particular quality attributes. Higher order structures usually people start giving importance when their molecule actually is formed. But I also think that if we start emphasizing on these parts much earlier during the development phase, probably we'll be in a better shape. Nevertheless, we will start our session with the talk from Professor Ashutosh Kumar. I have known him for nearly 20 years. When I was a master's student and went for a internship training at TIFR Mumbai, where he was pursuing his PhD. Ashutosh did his PhD from TIFR Mumbai, moved to Germany, and I was in Basel, so again we connected. So we met each other multiple times, and now with Biocon also we collaborate on multiple projects. So it is a pleasure for me to invite him to start this session and see some wonderful data which has also come out of a lot of his efforts towards biosimilar characterization. Dr. Ashutosh Kumar, stage is yours.
Thanks, Navratna, for introducing me, and thanks Ratnesh and his team for organizing this wonderful meeting in wonderful setting, right? So it's just on the beach. So today I'm going to show you what we are doing using NMR spectroscopy for in-formulation state, higher order structural characterization of biopharmaceuticals. How does this work? Slide changer. Just let me. Or I can use this. Not working. Hello, is it working now? Hello? Okay. Right, so not working. Otherwise, you can do one thing. If it does not work, you can change my slides. I should be fine. Right. So this audience does not require any introduction. That biologics are complex molecule and they are on rapid rise. You can see from one balloon to another. So it's a from small molecule to a small peptide to monoclonal antibody. It's complex. It's on like a exponential growth, even in approval, and all over the world, they are kind of becoming predominant therapeutics in coming age. So next, please. Right, so if you compare the characterization, I'll keep it short because audience is knowing everything. So biosimilarity development program based on the totality of evidence, like you require a robust analytical characterization for even for this, and some of the guidelines important to test the product and acceptance criteria for biologics product. That's what it is recommended by all of the regulatory agency. Next, please. So now, why NMR is important, that's what I'm going to illustrate more. It's one of the robust technique that give you detailed information about a complex biological molecule. The great part about that, it can give you atomistic assignment. Doing the multidimensional spectrum, you know information about each residue, even the atom in the residue. Like if we do say 2D NMR, we know from the each residue signal is coming from there, and that gives us opportunity to compare your innovator product with the biosimilar product. It's a highly reproducible technique. So every time you record the spectrum, if you are not changing any physiochemical property, you get highly reproducible spectrum, and that again give you advantage to show the similarity in more detailed way. The only challenge with NMR that it's sensitivity. It's one of the insensitive technique, therefore you require lot more sample than the usual other biological technique. Next, please. Right, so just get started. We start with just one-dimensional proton NMR spectrum, and here I am showing you if you just take an API, placebo, formulation 1 and formulation 2. Now in other orthogonal biophysical characterization technique, you just have one spectrum or one profile to match. Here you have so many peaks coming from the same peptide to compare. Now if you look at, these are the signal coming from placebo, so you can easily distinguish. But these signals, look at this signal, is coming from amide proton. This is present in say API, formulation 1 and formulation 2. And if you do analysis resonance by resonance, so you know that each atom, like here for tryptophan side chain has not moved. Amide protons have not moved. Aliphatic proton have not moved. So all those high similarity you are getting just comparing the one-dimensional proton NMR spectrum. And that gives us confidence that we can go more detail, and then next, please. And do the multidimensional spectrum to establish biosimilarity in robust manner. Next, please. So you can combine this with a heteronuclear experiment. So here what I'm showing you, this is called HSQC, heteronuclear single quantum coherence at a natural abundance, N15 and proton. You remember N15 at a natural abundance present is in percentage of 0.037%. But if you record overnight spectrum, you can get a beautiful spectrum, and each dot here represents one amino acid. Now with this resolution, you are quite confident what we are getting is going to be very accurate. But only problem that it took almost 13 hours to record. Next, please. So then we move ahead and exploited some of the one of the nice moiety that we have in amino acid. If you look at the protein, there are 6 amino acid out of 20 that has a methyl group, and methyl has a nice property. It has 3 protons, and those works like a rotamer, so it rotates like this. So it has a favorable relaxation property that can be used to design an experiment called transverse relaxation optimized spectroscopy, and you can do in really fast manner. So it's called so fast HMQC or HSQC. So exploiting these, one can record a spectrum, and if you plot those methyl groups in the higher order structure of a peptide or protein, you see they are separate, they are spreaded over whole protein sequence. So if you get a signal from these methyl groups, we have we can assess the whole structure of these protein or peptide. Next, please. So we recorded this 13 CHSQC or HMQC so fast manner using TROGI transverse relaxation optimized spectroscopy, and about 2 hours you can get an insulin spectrum, beautiful insulin spectrum. Now again here each peak represents one of the methyl groups. So you can assign even these methyl groups. For that you have to combine, of course, 2-deoxy and NOG. Next, please. And now you can see this signal is coming from isoleucine 2 or 10 or alanine B14C beta. So now we are talking in a residue specific manner or even the moiety specific manner, and this gives us lots of confidence that we can do a lot. Next, please. Okay, so I will now, here onwards, I am going to focus something that we did on diabetes related therapeutics, peptides, insulin, and this has emerged because of collaboration of Naratna with Biocon. So if you look, unfortunately, a country of yoga has become a country of diabetes, and all the coastal region wherever we are also, like it's lots of diabetic, about 24% in Goa and southern state or West Bengal, all these regions you have had high diabetes burden, and therefore, and diabetes is one such case where you need personalized kind of medication, right? Somebody requires quick insulin dose, somebody requires prolonged insulin dose, and all those. So the personalized medication cannot be accessed in a simple analytical characterization. You need really deeper characterization. Next, please. So because you see there are various insulin, many of you know rapid acting insulin like insulin Aspart, Lispro, that just picks up in 2 hours and lasts for about 6 hours. Then you have short acting insulin, regular soluble formulation that goes up to 8 hours. Then you have an intermediate acting insulin that goes about 20 hours. Long acting insulin like Lente, or prolonged acting insulin like Glargine, it once a dose or even 2 day a dose. And this dose is determined by altering their structure. So insulin generally is a monomeric protein, but it oscillates with a hexameric conformation. Now hexamer is stabilized by using zinc and protonium sulfate, or it is microcrystallized for making this prolonged acting or long acting insulin. Now if you want to establish the higher order structural similarity, you have to go and characterize in microcrystalline or biphasic state, and that's what we are doing in our lab. Next, please. Right, so if you are concentrating that protein to make a microcrystalline, there is a probability that they will be unstable. All of us know that at high concentration, protein will aggregate, precipitate, they form amyloids, they can go under liquid-liquid phase separation, and various things. It can degrade, so it can fragment or get oxidized. So these are even in the manufacturing stage. Even after manufacturing, in syringe, filling the syringe or storing it, there is a probability that it can get aggregate or degrade, or even during administration, protein conformation can change. Therefore, as Naratna made opening remark, that they should be characterized at every step of the process. Next, please. Sorry, can you go back? Yeah, so that's what I was mentioning to you. So typically what people do, if the insulin structure is in hexameric, to characterize, people change the equilibrium towards monomeric state by acidifying it, and then they characterize this active form of monomeric state. But this is formulated in a biphasic or microcrystalline form. So typically this is done by this, and if we change it to monomeric, we can do the analysis of this. Next, please. And we can even assess their binding. So we develop a method using STD methyl TROGI, where we transfer the magnetization from the IGFR, which is known to bind. This is our pulsicles, I will not go into detail. And these are epitopes where it can bind. So these are methyls basically. So we use this technique, STD methyl TROGI, to show that where insulin binds with the receptor. Next, please. Here. So now you can see insulin IGFR on and off. This is coming from the pulse sequence. And one can see what are the epitopes binding on insulin with IGFR. Next, please. And here, that's what we are showing here. This is insulin. This is a chain from the IGFR. This is the binding board. So not only, like if we do this experiment, not only we see the binding, we also access in a residue-specific manner the binding epitopes on insulin. Now you can make a variant and also test it whether it is binding in a similar manner or not. This is unprecedented. Typically, you do with SPR and you get a KD value of micromolar, but not in residue-specific manner. This techniques give you probability or a tool to assess that binding in a residue-specific manner. Next, please. Now, for showing biosimilarity, right, we have taken various formulations of insulin. We change it to monomeric state, and we did the 1D NMR spectrum. You can see all those peaks. You can match in the amide region, in the aliphatic region, and everyone. Here, using that methyl experiment, you can see that all the peaks are matching very well. There is one peak, right? Here is the difference, and that is coming from the formulation. Even that you can pick up that one peak which is different is because of one component that is different in the formulation. That's what it shows the differences. Next, please. Right, so you can do the statistical analysis to show similarity, and there are some methods. You keep going. There are some method called CCSD. So you can measure this chemical shift of proton and carbon. Keep going. Proton and carbon, and show that their deviation is less than, say, 0.02. That means they are highly similar. You can plot the correlation coefficient, and you can also show that they are very similar. So this is the CCSD, combined chemical shift differences. Depends upon the proton chemical shift, carbon chemical shift, and their intensity. So even intensity matching is captured here. Go next, please. One can do the principal component analysis by taking at least 3 batch of each of these, and one can see here the separation. Already we are getting more than 90%. Eclipse are quite overlapping. Using this data, you can even calculate one more statistical parameter called Mahalanobis distance. If it is less than 3, you know that our product is very, very similar. Next, please. Right, so that's all about small peptide. Can we really move into really large protein like monoclonal antibody? Problem with NMR that at a small molecular weight like a 8 kilodalton, the tumbling time is about 4 nanoseconds. So you get a really sharp peak, though overlapping, but you get a really sharp peak. As you increase the molecular weight, the tumbling becomes slow. Because of the tumbling slow and T2 is changing, you get a broad line. So if you reach to 50 kilodalton, you get a spectrum like this. Now this is a problem, and maps are 150 kilodalton. So you really get a broad line, right? So there is no probability of doing same NMR. Can we change a little bit? One thing, right? Maps are a stable molecule, so we can increase a little bit temperature. This is typically at 25 degrees. So if you increase temperature, we can speed up their tumbling, and we can achieve some sharpness. But then again, this technique that I mentioned to you, next slide, mentioned to you, can be used as a Troji. So here I will show how NMR can be used for showing at least some similarity. Here we use biosimilar and originator molecule of trastuzumab. We recorded something called diffusion order spectroscopy. We measure how molecule diffuses in solution by looking at the sharp peaks that I was discussing, and then we compared with the DLS. Both of them are showing more or less, these two orthogonal techniques showing more or less similar information. So this we published to show NMR, Doji NMR is one of the orthogonal technique for showing at least the diffusion coefficient same. Next, please. Now, as I was saying, increasing temperature, we can get a sharp line. So here one can show here originator 1 and biosimilar 1 and 2, 3, 4. Now we have a sharp line which we can use for again statistical analysis to show their similarity or dissimilarity in a regional specific manner. Next, please. Right, and since we are doing experiment at 45 degrees, so one can ask question: are you perturbing the structure? So we took it out experiment and we run on gel as SEC, and we find that all of them remain same, and that matches with the initial experiment, like initial sample before doing the experiment. So showed that at 45 degrees that does not change the structure at all, right? So we are still in safe zone while recording this. Keep going, right? So NMR can be also used same technique on map for accelerated stability test. So what you have to do? Keep recording the experiment, 1D spectrum at like whatever temperature we want. So you see at 0 weeks, all the originator and biosimilar are matching nice. If some of them are degrading, you will see in 12 weeks, some of them seems to be changing the peak. Now that's what accelerated stability test can be used NMR in a more robust manner. You can combine something called R2. So what you have to do, just in 1D fashion, you take the aliphatic region and do something called transverse relaxation experiment, and you plot the difference between like what about originator and biosimilar, and if this difference is very less, you know that nothing is changing, but if difference increases, then you know something is changing. This is collaborating with this. So decreasing R2 value shows that it's a fragmenting. Now your mag is fragmenting, and increasing R2 value shows that you are inducing aggregation. So that's what it shows by just doing 1D T2 transverse relaxation experiment. Next, please. Right, so that was all 1D about MAP. Can we do 2D? So here I was saying that methyls are again all over dispersed in monoclonal antibody. We can use this methyl in that STD TROG HSQC manner, and one can record spectrum overnight. Can you just, next please? Yeah, and here now we have more than 100 peaks. So now instead of 1 or 2 peaks, you are having a probe, 100 probes. Anything change, you can monitor. Please, next please. Yeah, go ahead. Right, so you can segregate those resonances that are coming from these methyl peaks, and one can see we can do the rest like a amino acid type tentative assignment. So here is methionine. One of the problem in monoclonal antibody that oxidation happens. So if any change happens in this area, you can easily pick up out that oxidation is happening. Next, please. Right, so you can again show the CCSD to show the biosimilarity between originator product and biosimilar product in a robust manner. Please, next please. And then you can combine that, we have a AUC that we can combine and look at that they are not aggregating or fragmenting. So you can see clearly 150 kilodalton single peaks is coming, and that can be clocked. Give me 2 more minutes. I have exciting news to share with you. So I was talking about this biophysics solution where you have some crystalline form, some soluble form, and nowadays people are believing that if you go in microcrystalline form, you are going to a robust biomolecular stable bioformulation that you have. So we use this biophysics solution, and again we establish the biosimilarity of solid and solution phase separately. So what we did, like we centrifuge and took out the microcrystalline parts separately and soluble parts separately. For soluble part we did liquid state NMR, for solid part we did solid state NMR, and this is 2 of my students who are here, they done the work. So what for solid state part we do, we spin at magic angle and detect on proton at natural abundance, and that we show the similarity here, that's what it's shown. Here for liquid and here for solid, and then you can go for a statistical analysis to show the similarity of these molecules. Keep going just quickly. Yeah, so here is the detail. Now, no, just one, go back. Yeah, oh no, go back. So what we showed that when we record this 2D for 2 different formulations, there was some change in the peak, right? Can you just go back 1 slide? More, here. There are some differences. So we combine this with wax and look at their packing was slightly different. Therefore, this solid state NMR spectrum was slightly different. So we develop another technique. With proton detection, and that we got a very nice resolution in the 2D spectrum. Next, please. Yeah, here is the pulse sequence. Go ahead. Here is the spectrum that we are getting. Next. Yes, that's the wax angle I was saying. So there is some differences in higher 2D value, and you can look at Soumya's poster for details. Because of time, I'll just close it here. So what I showed, NMR spectroscopy is an excellent tool for biopharmaceutical application. Initially, I showed you methyl HSQC for showing biosimilarity, higher order structural characterization. Doji NMR is for like getting the size of the molecule. You can combine this with AUC to find it out if there is a smaller fragment. And towards end, I showed you solid state NMR can be used for HOS of drug in the formulated state. Now, one can really monitor even MAB using NMR spectroscopy in very detailed manner, right, in a restrictive specific manner. Next. With this, I would like to thank my industrial collaboration, from various company who gave me sample. Go ahead. Next. And I would like to thank my co-workers. They work on these projects. Thank to NMR, which gives data, and I'm thankful to you for your attention. Next, please. And a special thank to Naratna for all the collaboration and bringing me to biopharmaceutical. He was the person who introduced me to biopharmaceutical words, and we are doing together some exciting science. So thank you very much.
Thank you. Thank you, Dr. Ashutosh. I think there is time for only one question. Only one. Okay. Ajinda has a question.
The small changes that you have monitored using the NMR as well as AUC, how they reflected in terms of the potency or the bioassay of the molecule?
How it has changed. So, you know, the aggregation causes the immunogenic response. Now, what we characterize is a structural change. Somebody has to come with me, join hand to show that this molecule, he is not into the immunogenic response. So, somebody from the... Yeah, so somebody who works in this, take this formulation, show how effective they are for causing immunogenic response.
Yeah, that would be ideal scenario to showcase the biophysical characterization, how they can impact the immunogenicity of the product. So I think that's what is something we can reflect from these
data.
Small changes that we are monitoring using biophysical techniques.
Certainly.
Yes, Rajendra. Thanks, Rajendra. Yes, so just to add on to what he said, so if the structural perturbation is on a site which can lead to immune response, that is something to be characterized, and that can be done in a combination of structural biology and functional assays, which is this technique alone cannot provide.
I can tell you one experiment we did for again insulin, where the structure of the molecule in our spectrum was slightly different. And then we did SPR. So nice one was binding with about 1.6 micromolar, and the crappy one was binding about 16 micromolar. So you see 10 times less. If your molecule is not correctly folded, 10 times less binding. And you don't want to make a molecule which requires higher dose to be injected in a person. So that's what we showed. I did not show you data today because of shortage of time.
Thank you. Yep.
Yeah. For such a study, you require a higher magnetic field. I have a 750 megahertz with liquid and solid both capability. So we can spin this microcrystalline formulation up to 42 kilohertz. Typically, we spin about 33 to 35 kilohertz for proton detection. Proton detection you cannot do at lower mass frequency.
So let's thank Dr. Ashutosh. Please hold on your questions. We will take your questions. Thank you, Dr. Ashutosh.